Thank you. And the next talk, I think the speaker should mute themselves. The next talk will be by Florian Cangemi on the integral discovery of a high energy tail in Cygnus X-3.
Yes, let me share my screen. Can you see my screen?
Yep.
Okay, perfect. Okay. So hello everybody, I am Florian Cangemi. I am a postdoc in Paris.
We don't see your screen now.
You don't see my screen?
No, we see your notes.
See your notes.
Your notes.
Just, we saw your desktop, so if you just go to full screen on the desktop, we should be able to cope.
Yes.
Just try sharing again and.
Do you see my screen now?
Yep.
Okay, and now do you see my screen?
Now your notes. Just go back to the previous thing and make it as large as possible, or like that. Now we don't see anything apart from a beautiful background.
Up.
Just go back to your background, pull it up, and we'll be able to cope.
And now I think it's working.
Yeah.
Okay, perfect. Okay, so I am Florian Cangemi. I am at LPNHE in Paris, and today I will present the work we did on the high energy emission of Cygnus X-3 with Integral. So as an introduction, I wanted to remind you some of the peculiarity of Cygnus X-3, because this is a particular source that can pass through 6 different spectral states. So here on the right, you have the hardness intensity diagram from Colonel et al. In 2010, where they defined 6 different spectral states. So you can see here the division. And this classification is based on the X-ray spectrum, but also the radio flux. So here on the left, you have a sketch representing the radio flux as a function of the soft X-ray flux. So the first state is called the cation state, where the radio flux is low and the X-ray spectrum is dominated by thermal comptonization. But we observe compact radio jets. So in the radio spectrum, we see a flat radio spectrum. Then we have the transition state, which is basically the same state as the cation state, but we have a higher radio flux and a higher soft X-ray flux. Then the source passes into the flaring hard X-ray state when we start to observe discrete minor ejection. And at this point, the source can either go back into the transition and the cation state, or enter into the hypersoft state, where the spectrum is the X-ray spectrum is completely dominated by the emission from the disk, and we do not see radio emission in this state. And this is after that the source enter in the flaring soft X-ray state and the flaring intermediate state when we observe a very strong ejection. So we see one of the particularity of Cygnus X-3 is that we observe the strongest ejection from the softest state to harder state, contrary to other black hole X-ray binaries. And the other particularity of this source before this study was that it was detected up to 80 keV, even for the hardest state. So very little was known about the high energy emission for this source. So this is why we wanted to use Integral, because it is a satellite that can be sensitive up to, let's say, 2 MeV. So we wanted to investigate the high energy emission of Cygnus X-3. So here I'm showing you the 16 years light curve of Cygnus X-3. So we gather all the available data of Cygnus X-3. So here you have the light curve between 3 and 25 kV. So each dot corresponds to one integral pointing. And then we use the previous classification from Colliona in 2010 to classify each integral observation into the different states. So this classification was based on RXT PCA data, but we adapted it to classify integral data. And the goal is to do a state resolved analysis at high energy. So here I'm showing you the stacked image over 16 years of data between 150 and 200 kV, where we see that for the first time we are able to detect Cygnus X-3 at 8 sigma. And then so we created 6 different spectra for the different states. So at low energy, we use the GEMIX monitor, and at high energy, we use the imager IBIS and the spectrometer SPI. So we see here for all of the spectrum that we have a significant contribution of a non-thermal component. So either in addition of the thermal comptonization, for example, in orange in the cation state, or in addition to the emission from the disk. So for example, in the hypersoft state here, we see the emission from the disk, and we see also this non-thermal component. So what is the source behavior at high energy? So in order to try to answer to this question, we followed certain methods separated in 3 different steps. So the first step is to focus on the 3 and 50 kV band. So we use a simple phenomenological model to fit the data. So basically here, for example, we use a cutoff power law with absorption, reflection, and the iron line. Then we add the data above 50 kV, and we let the parameter vary in order to see if we need an additional component at high energy. And what we found is that for the quiescent and the transition state, you see that we observe strong residuals at high energy, and we need an additional power law component in order to fit correctly the data. So the origin of this high energy component in X-ray binaries is largely debated, and there are 2 main scenarios that try to explain it. So the first one proposed that, in fact, what we see in the hard X-ray is the extension of the synchrotron emission from the jet, so the emission from the jet's base. And the other scenario proposed that, in fact, we have a hybrid corona where there is a thermalized population of electron and an accelerated population of electron, and this is what we see at high energy. So we tested the first scenario to see if our power law spectrum is consistent with the emission from the jet. So here you have the average radius spectrum. You have in blue the infrared emission. We also add the emission from the companion star. And in gray, you have as a reference the location of the synchrotron cutoff of JX339-4. So if we use this jet constraint given by the infrared emission, and if we extrapolate as a form of a power law to the X-ray, we would have a photon index of 1.8. And this is not consistent with the power law that we measure in this state. We measure a photon index of 2.2. And alternatively, if we extrapolate this power law that we measure to the radio emission, we see that the flux that we would have would be higher than the flux measured. So what we see seems to not be due to the jet. Of course, this is a rough estimation. This is not a precise jet modelization.
3 minutes.
Okay, thank you. Then we wanted to investigate the other scenario, which is an hybrid thermal non-thermal corona. So we use the Ekper model, which introduce the disk emission, the Comptonization emission, Bremsstrahlung, and pair production processes. And we see here, so the result of this fit, that the data is correctly fitted by this model, and we found consistent results with previous study. So I won't go into details of the parameter that we found, but the global trend that we see is that as we get softer, we see that the thermal comptonization shrinks, and the disks start to appear here in the flaring hard X-ray state, and we see this non-thermal component here in every state. And if we want to focus on the electron injection index, which represents how much the electrons are accelerated inside the corona, we see that we obtain a smaller value for the flaring intermediate state and the flaring soft X-ray state, meaning that we have a more efficient acceleration mechanism in the states. So the mechanism that could accelerate electron could be shocks due to the intense stellar wind, or we can imagine that in a geometry when the corona is at the base of the jet, the mechanism that triggers the jet is also responsible for the electron acceleration inside the corona. So this is my summary slide. So what we did is that we use the whole integral dataset to detect Cygnus X-3 for the first time up to 200 kV. Thanks to the classification of Colonel et al. In 2010, we did a state resolved analysis, and we detect an additional power law component in the harder state, so in the quiescent and the transition state. And we see that this emission is not consistent with synchrotron emission from the jet, but this could be consistent with a non-thermal origin of accelerated population of electron in the corona. And I'm finished. Thank you.
Thank you. I see a question here in the back of the room, and there's also one online.
Hi, Florian. Ilek here. Thank you for the great work. I had a question concerning the acceleration mechanism. You say that it's associated to that it's stronger during ejection. Do you have any clue whether that would be possible to constrain the mechanism behind this particle acceleration?
I don't know how we can do that, honestly. As I said, there is a paper from Sotzek in 2008 where they also see a correlation between the flux of the non-thermal component and the radio emission. So there is directly a link between this non-thermal emission and the radio emission, but I don't know how we could constrain the mechanism behind it, honestly.
Okay, so that's still possible that it's either magnetic reconnection or
yes, of course. Yes.
Okay.
But in the model that we use here, Ekper, we do not introduce magnetic field. So we can't have magnetic reconnection here, but there is another version of this model which is BELM, where there is the magnetic field and we can determine the value of the magnetic field. And if it is strong enough, we could have a magnetic reconnection. But we didn't test with this model yet.
Okay, thank you.
The second question is by Asaf Per. Mukesh, I see you have your hand up, but we will run out of time. So can you please ask your question in the Slack?
Right. So thank you. Actually, for this slide, it's kind of a continuous question to what was just asked. It seemed that the high energy flux is not changing between the different states, right? That you're showing here. So how can you explain that? If
I
I
have-
look at that plot that you just had.
I have the value of the flux, but they are not there. I think there is an evolution of the flux between the different states. For example, in the hypersoft state, the flux of the non-thermal component is very low compared to the cations and the other states.
But if I read the y-axis, which is a bit hard from here, it seems that it's the same order of magnitude.
I can maybe find these fluxes. Can I share another screen, maybe?
I think we're running out of time. Perhaps let's
do you see?
let's move that over to the Slack if necessary.
Okay.
Okay. Let's thank the speaker again.